Welcome to the third part of basic law of thermodynamics. The second law of thermodynamics, Joule's experiment, amply demonstrates that the energy when supplied to a system in the form of work can be completely converted into heat, work transfer internal, energy increase, heat transfer. Second law of thermodynamics, Joule's experiment. Joule was a scientist. Joule's experiment amply demonstrated that the energy when supplied to a system in the form of a work can be completely converted into heat. This is what was the second law. But the complete conversion of heat into work in a cycle is not possible. So, heat and work are not completely interchangeable form of energy. So, the work is said to have a higher grade energy and heat is said to have a lower grade energy. The complete conversion of low grade energy into a high grade energy in a cycle is impossible. That is what Joule in his experiments demonstrated. Okay? This is also very important. The complete conversion of low grade energy into a high grade energy in a cycle is highly impossible. The second law states that not all the energy can be converted into a useful form. So, the first law said the energy will be transferred from one form to the other form. In the second law, it states that not all the energy can be converted into a useful form. So, that means to say there is a loss in the conversion and there is a natural tendency for a system to evolve toward a state of increased disorder or randomness. So, which is quantified as entropy. So, the conversion whatever happens leads to a natural tendency for the system to evolve towards the state of increased disorder. In the second law of thermodynamics chapter, we will keep focusing towards entropy. And entropy, if you want to correlate with the previous knowledge, when we draw a PV diagram, we also draw a TS diagram, temperature entropy diagram. So, that is what is entropy. Entropy is nothing but represented as S. What are the aspects of the second law? It helps to identify the direction of the process. That is very important. In which direction the energy is getting converted. Next, it establishes condition for equilibrium. The third thing is it also asserts the energy has quality as well as quantity, both. It also asserts that the energy has quality as well as quantity. Quantity means it also talks about the magnitude. These are all the aspects of second law. Then it is also useful in determining the theoretical limits for the performance of the heat engine and refrigerator. So, if you want to work on the efficiency of the machine, so that is dealt in the second law of thermodynamics. Why is that efficiency important? I should know, I apply a certain power inside, what will be my energy conversion and what will be the loss. So, it is also used in determining the theoretical limits for the performance of heat engines and refrigerators, defining a temperature scale independent to the properties of any thermometric substance is also an aspect of second law. So, in conclusion, second law tells that not all the energy which is getting converted into a useful work, there will be some amount of deviation. So, that deviation is the tendency for the system to evolve towards a state of increased randomness, right. So, then these are the aspects. You have a hot body, then you have a cold body, right. The generally temperature gradient is there. So, the energy gets transferred from hot body to a cold body. So, that is what I have said here in the direction heat transfer. So, I said here that it identifies the direction of the process, which is delta Q, heat. Then there is a randomness, I said, entropy, that is delta S, entropy, which is nothing but delta Q, heat transfer, by the temperature. Okay. So, this tries to help in determining the limits, thermal limits of the performance of the system. So, now let us try to understand the concept of thermal energy reservoir, which is shortly or abbreviated as TER. It is a hypothetical body with a relatively large thermal energy capacity that can supply or absorb finite amount of heat without undergoing any change in temperature. This is a hypothetical body wherein relatively large thermal energy capacity can be absorbed. From the sun, you have heat which is trying to hit at the earth. So, a large thermal energy capacity that can supply or absorb finite amount of heat without undergoing any change in the temperature. Example, as I told you, is ocean, river, atmospheric air. The TER that supplies energy in the form of heat is known as the source. So, now we are trying to introduce the concept of source and sink. Source is the supply of energy and sink is a place where it absorbs energy. The thermal reservoir are essential in the analysis of Carnot cycle or a refrigerator and other idealized system, which provides boundary conditions that help in determining the maximum possible efficiency. So, from source to sink, how is the energy getting transferred? We are trying to use Carnot cycle and see what are all the conditions with when applied you can try to get the maximum efficiency, because every engine would like to run at its maximum efficiency, or we would like to run the engine at maximum efficiency. If the engine has to run at maximum efficiency, then there are only two things: either you move the engine or you operate the engine in a process parameter optimized way, energy efficient way, or you try to work around the engine. So, that means to say you work around the engine means the surrounding or the boundary. So, that is what providing boundary conditions that help in determining the maximum possible efficiency of thermodynamic device. So, if you want from a sink, there is energy or a engine there. This engine, when you apply a work to that engine, it will try to increase and go to the source. So, this is cold QC, this is hot. So, the second law of thermodynamics is essential for understanding the limitations and the directions of energy transform. The second law of thermodynamics have two basic statements. One is called as Kelvin-Planck statement, the other one is called as Clausius statement. So, Kelvin-Planck statement, this is with reference to heat engine, and Clausius statement is with reference to refrigerator and heat pump. Now, let us understand what is a heat engine. Heat engine is a cyclic device which is used to convert heat to work. So, there is a heat. So, you see here source, there is a sink Q1, Q2. So, you can see the direction which it comes, and in the heat engine you try to get the work done. The heat engine can be characterized by the following points. They receive heat from a higher temperature, they get converted the heat into work usually in the form of rotating of shaft, turbine engine. The rejected whatever is residue air which is with heat, which is called as waste, is sent to the lower sink. They operate on a cycle. The heat engines are fundamental to many heat conversion systems, which include internal combustion engine, steam turbines, gas turbines and jet engines. The basic working of a heat engine involves 4 steps. Basically, the first step is heat input, which is called as Q in, is absorbed from the higher temperature reservoir. Part of the energy is converted into work by expanding a working fluid. So, it can be steam, it can be gas, whatever it is. Then the next one is the working fluid of the system. The last one is heat is rejected, which is called as Q out, to a lower temperature reservoir. The engine then returns to its original state to repeat the cycle. So, it can go repeatedly to form a cycle. So, if you want to calculate the thermal efficiency of a heat engine, which is got by this efficiency term eta of a heat engine, is defined as a ratio of useful work output to the heat input. So, useful work output W net by Q in, which is equal to 1 minus Q out by Q in. Through this, we always try to get the efficiency of the system. This equation shows that there is always a heat which must be rejected, which means that no engine, heat engine, can have 100% efficiency as per second law of thermodynamics, which is also true in reality. The theoretical maximum efficiency, the first one we did for HE, right, heat engine. Next one we are trying to take for Carnot. So, efficiency of a heat engine operating between two temperature reservoirs is given by Carnot efficiency. So, eta Carnot is equal to 1 minus T cold by T hot. T hot and T cold are the absolute temperatures in the sink and source. The Carnot cycle sets the upper limit of the heat engine performance and serves as a benchmark for evaluating the real engine. That is why we always talk about Carnot cycle. What are the components? Heat source, it supplies thermal energy at a higher temperature. Working substance is typically a gas or a vapor that undergoes expansion or compression. Then engine mechanism is converting expansion of the working substance into a mechanical work, like your heat engine. Then the heat sink is also the same. We have added one more term which is called a cycle controller, manages the cyclic process and controls timing. There are common heat engines. One is Carnot cycle, which is ideal, reversible. Then it is Otto cycle, used in petrol engine. Diesel cycle is used in diesel engine. Rankine cycle, which is used in steam turbines. Brayton cycle, which is used in gas turbines and jet engines. So, this is Carnot cycle is ideal and reversible. So, when we try to draw a PV diagram, so we can see from A to B it is isothermal, from B to C is adiabatic expansion. So, A to B is isothermal expansion, B to C is adiabatic expansion and C to D is isothermal compression and D to A is adiabatic again compression. So, isothermal is Q in, which happens between A to B, and C to D there is always a rejection. at B to C and A to D, the adiabatic Q is always equal to 0. So, you can see here schematically a hot reservoir where Q is pushed into a engine, and then you try to get a Q out where it is a cold reservoir. You have a weight. When the heat is applied, the gas expands and the weight increases, or weight moves high, or the weight is pushed to a higher level. Let us now try to understand the concept of heat pump. Heat pump is another cyclic device. Heat engine is a cyclic device. Heat pumps are also cyclic device. They are used to transfer heat from a lower temperature to a higher temperature. So, the objective of the heat pump is to maintain a heated space at a high temperature. This is accomplished by absorbing heat from a lower temperature source, such as a cold outside air in a winter, and supply this to a high temperature medium such as a house. So, there we use a heat pump. So, heat pump and heat engine, which is used to convert heat from a lower temperature medium to a higher temperature medium, or from a low temperature medium to a high temperature medium. So, the objective of a heat pump is to maintain a heated space at a high temperature. So, here the work is done such the heat pump is operating from a lower temperature, it goes to higher. Unlike heat engine that converts heat into work, or refrigerator that cool a space by removing heat, a heat pump is primarily used for heating purpose, delivering heat to a warmer space by extracting it from a colder environment. So, you can see heat pump and heat engine, they are different. This is especially used for space heating in winter, where ambient outside air, soil or water serves as a cold source and the heated indoor space is a hot sink. So, the heat pumps operate on a reversed Carnot cycle, or more practically on the vapor compression refrigeration cycle, much like a refrigerator or a air conditioner. So, a vapor compression refrigeration cycle. The system includes 4 components: compressor, condenser, expansion valve and an evaporator. So, we will see the schematic diagram of a heat pump. So, you have a compressor which tries to compress air, raises the pressure and temperature of the refrigerant. Then subsequently, you have a condenser. The condenser releases the absorbed heat into the indoor. So, this part will be inside the building. So, this is indoor. So, then once it has done its job, then it passes through the expansion valve and goes to the evaporator. Evaporator absorbs heat from the cold outdoor environment. Right? So, the system starts from this way. So, from the blue, the heat source is going away. So, you will have a compressor. So, the compressor gets its infeed from an evaporator. The evaporator absorbs heat from the outdoor environment. Compressor increases the pressure and the temperature the compressor does. Then the condenser releases the heat absorbed into the indoor, and then it goes to an expansion valve. From the expansion valve, it goes to the evaporator. So, in heating mode, evaporator absorbs heat from the cold outdoor environment. Compressor raises the pressure and temperature. Condenser releases the absorbed heat into an indoor space. Expansion valve reduces the pressure. So, if you go by it, expansion valve reduces the pressure, compressor pressure increases, right. The evaporator, the expansion valve reduces the pressure before the refrigerant enters into the evaporator. So, the heat pumps are widely used in residential and commercial heating, water heater and industrial drying or dehumidifying systems. Everywhere we use the heat pumps. Heat pumps are slightly energy inefficient as compared to heat engines. They are energy efficient, reduce dependency on fossil fuel and can often reverse operation to act as a air condition in summer, making it as a dual purpose. Today we have air conditioners which are available hot and cold. So, it works on this principle. So, we have a heat pump, right. This is called as a heat pump and these are the 4 components. Now, let us go back to Kelvin Planck statement of second law. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So, this is what Kelvin Planck statement it crudely makes. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So, you can see a thermal reservoir which where there is a work cycle which is done. The system undergoes the thermodynamic cycle here. So, it is not there. So, the Kelvin Planck statement asserts that no heat engine can operate in a cyclic process and convert all heat it absorbs from a higher temperature reservoir entirely into a work without rejecting some heat to a lower temperature reservoir. So, you can never convert all the heat which is grabbed from a heat source and get it back into the system without undergoing certain amount of loss. In other words, it is impossible to achieve 100% thermal efficient cyclic heat engines. In figure below, that even under ideal condition, the heat engine must reject some heat to a lower temperature reservoir in order to complete the cycle. That is, no heat engine can convert all the heat it receives to a useful work. For example, the reservoir at 100 degrees, there is a gas at 30 degrees, there is a load. So, when the gas expands, right, when the gas expands, the reservoir you try to inject it, the heat is about 100 kilojoule. So, when it is given to the gas expands, the weight is lifted and they are putting the upper limit and lower limit. So, you can see that the weight is, it is lifting and it is around about 15 kilojoule, right. So, it expands and reaches this point, and because of the load whatever you apply, it compresses the gas. Once the gas is compressed, the gas temperature is brought to 30 degrees, it rejects to the reservoir back at 20 degrees. The heat out will be 85 kilojoule. So, this limitation on the thermal efficiency of a heat engine forms the basis of Kelvin Planck statement of second law of thermodynamics. The heat engine must exchange heat with a lower temperature sink as well as a higher temperature source to keep operating. So, Kelvin Planck statement can also be expressed as no heat engine can have a thermal efficiency of 100%, or as for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. So, this is the repeat of the previous one. So, here we see a thermal energy source where it is 100 kilowatt is given. So, there is a heat engine. So, a heat engine there. So, QL and work out is there 100 kilojoules. The heat engine that violates the Kelvin Planck statement of the second law is derived here. So, the application of Kelvin Planck statement: internal combustion engine, external combustion engine. Internal combustion engine is car, truck, motorcycle, you will know. External combustion engines are such as steam engines in thermal power plant, where the heat from burning fuel is used to produce steam, which then drives a turbine. Not all the input heat is converted into work. Some of them are released to a condenser or a cooling system. Gas turbine is another application. Power plants. Power plants are which includes thermal, nuclear and geothermal plants, which uses heat to generate electricity. Right? So, here also these plants don't operate at 100%. The refrigeration and heat pump analysis, the statement is used to compare and calculate the efficiency of engine, refrigerator and heat pumps, emphasizing the necessity of a heat sink for continuous operation. Now, let us move to Clausius statement. It is impossible to construct a device that operates in a cycle and produce no effect other than the transfer of heat from lower temperature body to a higher temperature body. The Clausius statement, on the other hand, emphasizes that the heat cannot flow spontaneously from a colder body to a hotter one without external force being done on the system. So, from cold to hot, if it has to go, there has to be some work done. So, the Clausius statement, on the other hand, emphasizes that heat cannot flow spontaneously from a colder body to a hotter one without external work being done on the system. This explains why refrigerators and heat pumps require energy input to move heat against its natural direction. This is a point which every time is asked in interviews. This why refrigerators and heat pumps require energy input to move heat against the direction. So, this is the reason. So, here in Clausius statement, from a cold air at T2, you try to move to T1, where in which you try to apply a work on top of the system HP and get it transferred. This explains why refrigerator and heat pumps require energy input to move heat against its natural direction. A refrigerator that violates the Clausius statement of the second law. So, a refrigerator that violates a Clausius statement of second law is given here. So, this is the refrigerator that violates the Clausius statement of second law. So, this way the net effect on the surrounding involves a consumption of some energy in the form of work, in addition to the transfer of heat from colder body to a warmer work. That is, it leaves a trace in the surrounding. Both Kelvin Planck and Clausius statement of the second law are negative statements, and the negative statements cannot be proved. Like any other physical law, the second law of thermodynamics is based on experimental observation. To date, no experiments have been conducted that contradicts the second law, and this should be taken as sufficient proof of its validity. So, these two statements are only to say how is this law still getting accepted in reality. So, applications: refrigerator and heat pumps are part of Clausius statement. Air condition is an example. Thermodynamic analysis. The Clausius statement is fundamental in analyzing and designing thermodynamic cycles such as Carnot cycle, and in determining the thermodynamic limit of the efficiency of the heat engines and refrigerator. So, now there is a possibility of Clausius statement. So, Clausius statement, equivalency of two statements. Kelvin Planck and Clausius statements are equivalent in their consequences, and either statements can be used as an expression of the second law of thermodynamics. Any device that violates Kelvin Planck statement also violates Clausius statement. So, if it violates Kelvin Planck, Clausius statement is also violated, and vice versa. That is what is explained here. So, the equivalency of Kelvin Planck and Clausius statement. The equivalency of a statement is demonstrated by showing that violation of each statement implies the violation of the other. So, from here you can see from Q2, the Clausius is obeyed here in this first one, and the Kelvin statement is violated here. So, you can see T1 He is there and it gives you W. This W comes to Hp, and here it goes from Q2 go plus W here, and then it goes to T1. Right. So, this is violation of Kelvin-Planck statement. So, the heat engine Q1 goes to Q2 where Q2 equal to 0. So, it is violation. So, you can take it from here T1 goes to He where W equal to Q1, and then this Hp is operating. So, from here, so Q1 plus Q2 is there. So, the last one is violation of Clausius statement is Q2, Q1, and there is no work done at all. The second, thus violating Kelvin-Planck statement has led to the violation of Clausius statement. Violation of Clausius statement leads to the violation of Kelvin statement. In the previous one, it is violation of Kelvin-Planck leading to Clausius. So, here it is violation of Clausius statement lead to the violation of Kelvin-Planck. So, you can see here T1, T2. So, there is Hp pump, the work is done is 0. So, the Q1 leading to Q1. So, in the second case Q1, Q2, we have He where Q work done is equal to Q1 minus Q2. The next thing is T1, T2. So, where Hp, you can see heat pump, the work is 0 here. So, and then it has taken Q1, from Q1 you tap it and give it to He, and then this is Q2 where W equal to Q1 minus Q2. So, here it is the Clausius statement are getting invalid. So, violation of Kelvin statement is He, you give a Q1 and then you draw Q2, W is equal to Q1 minus Q2. So, all these things equivalent circuits are drawn to say you that one statement leading to the violation of the other. So, thus the violation of Kelvin-Planck statement has led to the violation of Clausius statement. At the first sight, Kelvin-Planck's and Clausius statement may appear to be unconnected, but it can be easily shown that they are virtually two parallel statements and the second law of the second law and are equivalent in all aspects. So, that is why we always take these two laws and go. The equivalency of the two statements will be proved if it can show that the violation of one statement implies the violation of the other. The last part of this lecture, we will try to discuss about the reversibility and irreversibility. The second law of thermodynamics enables us to divide all processes into two classes: reversible and irreversible, ideal process and natural process. A reversible process is one which is performed in such a way that at the conclusion of the process, both the system and the surrounding may restore to the initial state without producing any change in the rest of the universe. The reversible process is carried out infinitely small with an infinitesimally gradient, so that every state passed through the system is an equivalent state. The irreversibility of the process may be due to either one of these two states. One is lack of equilibrium during the process. There can be mechanical inequilibrium, thermal inequilibrium, or chemical, right, between the system and the surrounding, between two systems, or between two parts of the same system, causes a spontaneous change which is irreversible. Involvement of dissipative effect is the irreversibility of a process may be due to the dissipative effect, in which work is done without producing an equivalent increase in the kinetic or the potential energy. So, irreversibility of the process may be due to the lack of dissipative effect, in which the work done without producing equivalent increase in kinetic and potential energy of any system. So, this is dissipative effect. So, there can be two effects, right, irreversibility process can have. Thus, to conclude, we have seen in this lecture the state and explain the first law. Energy is a property of a system. First law of thermodynamics, its limitation. Second law of thermodynamics, wherein which we had seen Kelvin-Planck statement, Clausius statement. Then we try to see reversibility and irreversibility. Friends, as I told you, the numerical problem will be solved during the tutorials. These are the references which we have used for making this slide. Thank you very much.